Welcome to EPG Pathshala. In this module, we will be studying about the thyristors. In general, we are more familiar with various types of thyristors and their use. But in practice, for high voltage applications, transistors cannot be used because their high voltage capability is limited to 1000 volts. At higher voltages, we have to use the thyristors. In this module, we will be studying symbol, structure and IV characteristics of the various thyristors. If we say thyristors, it means those are conventional thyristors. Conventional thyristors have limitations. The main limitation is turn-off capability. When we say conventional thyristor, it has turn-on capability. But their use is comparatively very simple. But for some applications, you need something different types of thyristor which will be having the turn-off capability. We will be studying the thyristor with turn-off capabilities also. In addition to this, we will be studying the turn-on and turn-off mechanisms also. We will be going through the various applications of the thyristors. We have already studied the silicon control rectifier, which is the basic thyristor, that is conventional thyristor. In this module, we will be studying various types of thyristors. We can classify the thyristor according to the control and direction of the thyristors. Mainly, thyristors are unidirectional. So, we will be studying unidirectional thyristors. In unidirectional thyristors, there are two types. First is controlled turn on, but uncontrolled turn off, and second is controlled turn on and turn off also. If we see controlled turn on, there are conventional thyristors. First thyristor is phase control thyristors, mainly known as PCT, amplifying gate thyristors, fast switching thyristors, FET controlled thyristors, light activated thyristors and reverse conducting thyristors. If you say controlled turn on and turn off also, mainly it is called as turn off thyristors. These are gate turn off thyristors, MOS turn off thyristor, emitter turn off thyristors, MOS controlled thyristors, integrated gate commutated thyristor and static induction thyristor. Apart from these thyristors, there are various types of thyristors which can be used, but here the discussion will be limited to these thyristors. All the thyristors still we have seen, these are the unidirectional control thyristors. There are bidirectional control thyristors also, but they are limited. The first is TRIAC, which is called as the bidirectional triode thyristor, and second is bidirectional phase control thyristor, that is BCT. First we will see the unidirectional thyristors with control turn on, but uncontrolled turn off. PCTs, amplifying gate, asymmetrical SCR and fast switching thyristors. Apart from that, we will be studying FET control, LASCR and RCTs also. First, we will see the SCR. So, basically it is used for phase control, that is why it is called as phase control thyristor. These are slow thyristors, turn off time is of the order of 50 to 100 microseconds. These are suitable for low switching applications, hence those are also called as converter thyristors. It has low cost, high efficiency, rugged and high voltage and current capability. These are extensively used in DC to AC converters, mainly for 50 to 60 Hz supply. These are also used in high voltage transmissions. Amplified gate thyristors. These are also PCTs, but it has additional characteristics, that is very high gate sensitivity. It has inbuilt two thyristor. One thyristor is auxiliary thyristor, other is main thyristor. Main thyristor carries all the current. Gate signal is given to the auxiliary thyristors TA as shown in the figure. T amplifies the current and drives the main thyristors. It has a high dV by dt, that is 1000 volt per microsecond, and dI by dt limited to 500 ampere per microsecond. Since dV by dt and dI by dt are high, the limiting inductor value decreases. Fast switching thyristors. These are the SCRs only, but turn off time is less, of the order of 5 to 50 microseconds. These are used in high switching applications. Since these are used for inverters, these are called as inverter thyristors. It has a high dV by dt and high dI by dt. It has fast turn on and turn off time. Because of that, it reduces the size of the commutating components. Asymmetrical thyristor. It is also called as asymmetric silicon controlled rectifier, that is ASCR. It is fast switching thyristor. It has all advantages as a fast switching thyristors, but it has limited blocking capability, typically 10 volt. The symbol, the structure is shown in the figure. The IV characteristics is similar to SCR, but IV characteristics shows that the reverse characteristics is different than the SCR. So, it reverse voltage capability is low. Its turn off time is typically 3 to 5 microseconds. Due to fast switching, it is also called as inverter thyristors. It has reduced reverse blocking capacity due to thin middle layer, that is N layer. N layer consists of two layers, N plus, that is low resistivity region, and N minus, that is high resistivity region. The applications of the asymmetric thyristors are DC motor control, force commutated inverters, battery charging, etc. LASCR, that is light activated silicon controlled rectifier. This we have already studied. Its symbol is shown in the figure. Its structure is PN, but with one window. This window is necessary for the exposure of light. Its equivalent circuit is also shown in the figure. It is PN transistor with photodiode. These also we have studied already. These are also called as light triggered thyristor. Turn off time is high, 50 to 100 microseconds. Used in low switching application, provides isolation between control and power circuits, hence used in high voltage applications. It has high dV by dt, but low dI by dt. These are widely used in high voltage DC transmission system. These are also used in reactive power compensators, high voltage drives, and high voltage pulse generators. The next ASCR is FET Controlled Thyristors. In this there is inbuilt N-channel enhancement MOSFET across thyristor as shown in the figure. It can be turned on by applying gate to cathode voltage, typically 3 volt. Triggering current of T1 generated internally. Less drive power is required due to the voltage control. It has high switching speeds, high di by dt and dV by dt as compared to phase controlled thyristors. These are not much used in practice. Next thyristor is reverse conducting thyristor. The symbol is shown in the figure and structure is also shown. So, it has two sections. First is thyristor section and another is diode section, which is shown at the right hand side of the figure. It is an asymmetric punch through structure with an integrated anti-parallel diode. Therefore, it requires very short time to turn off. It has high forward blocking voltage, current rating up to 500 ampere, but reverse blocking voltages at transients are limited to 30 to 40 volt. Advantages of RCT: heat sink size is reduced, undesired loop inductance effect is eliminated because of inbuilt diode, unwanted reverse voltage transient reduce better commutation. There are various applications, but main applications of the RCTs are DC drives for traction, DC choppers, high power inverters. These are the conventional thyristors with turn-on capability, but this cannot be effectively used for inverters. Till now, we have studied thyristors with turn-on capability only, but in applications such as inverters, we require circuits with turn-off capability. So, now we will be studying the turn-off capability thyristors or thyristors with turn-off capabilities. There are various types of thyristors available, but the main thyristors are generally limited to 6 to 7. First is GTO, which is a basic type of turn-off thyristor. Then MTOs, ETOs and IGCTs are the derivatives of the GTOs. Then MOS Controlled Thyristor. Last is static induction thyristors. We will be studying first the gate turn-off thyristor. The symbol of gate turn-off thyristor is shown in the figure. Gate turn-off thyristors has highly interdigitated gate structure with no regenerative gate. Additional N plus layer near the anode forms the turn-off circuit between the gate and cathode in parallel with turn-on gate. Because of that, a large initial gate trigger pulse is required to turn on the thyristor. The symbol of the thyristor is like SCR. If you see the structure, as already shown, it has Pn plus Npn structure. Turn on of the GTO can be viewed as shown in the figure. There are two transistors Q1 and Q2. Q1 is NPN transistor, Q2 is PNP transistors. When we apply forward gate current to the Q1, Q1 will turn on first, then it will drive the Q2, that is PNP transistor, and thyristor will turn on. So, this is a turn on mechanism. If you see the turn on characteristics of the GTO, it is complicated than the normal SCR, which is shown in the figure. From the figure, it is visible that initially we require the high current pulse to the GTO with high di by dt, that is high dig by dt, that means rate of change of gate current. After giving the initial gate pulse, we require the constant gate current given to the GTO gate. Now we will see the turn off sequence. Turn off is much difficult to understand than turn on. So, to turn on the thyristor, negative gate pulse is applied to the thyristor. After applying negative gas, some current will be diverted toward the gate and some current will be diverted to the cathode. Now, if you see the diagram, the current levels are high. So, here one other parameter comes in the picture, that is turn off gain. Turn off gain of the thyristor is defined as anode current divided by gate current. So, 1/4 of the thyristor current is diverted toward the gate. So, that is why it will turn off immediately. If you see the turn off characteristic, that is switching characteristic, it is complicated. So, it will require high peak negative gate current with high dig by dt as shown in the figure. GTO takes long time to turn off. So, initial turn off is fast, but after some current there will be tail current, so which is long. So, that is why effective turn off time of the GTO is higher, so which limits the high frequency operation of the GTO. These are the parameters shown of the GTO turn off characteristics. The gate drive circuit is shown in the figure. It consists of two power supplies, V1 and V2, two transistors T1 and T2. These are the MOSFETs. There are various resistors and capacitors which are used here. These two transistors T1 and T2, which are used to turn on and turn off the gate respectively. The resistor R2 and C2 shapes the initial gate pulse. R1 determines the continuous gate current. RG guarantees the minimum blocking capability of the GTO. There is supply voltage, that is V2. It is -8 into -22 volt. The supply voltage V2 is used to turn off the GTO faster. Advantages of the GTO: it has high current and voltage capability. It has low conduction loss, but higher than SCR. Force commutation circuit is not required because of turn off capability. Due to elimination of commutation chokes, acoustic and electromagnetic noise is greatly reduced. Since it is a fast turn off, it permits high switching operation of the GTO than conventional thyristors. Because of high switching frequencies, it has improved efficiency. In voltage source inverters, a fast recovery diode is necessary across a thyristor. In such cases, asymmetric GTOs are used. Asymmetric GTO is nothing but a heavily doped N plus layer, which is also called as buffer layer, introduced at the end of the N layer. So, it does not have reverse blocking capability. Reverse blocking capability of asymmetric GTO is obviously very low. There are some advantages of asymmetric GTOs over symmetric GTOs. It has low on-state voltage drop and higher voltage and current rating in forward direction. There are certain disadvantages. Non-uniform turn off leads to the poor reverse bias SIP operating area. Therefore, dV by dt snubber is must. In case of non-uniform turn on, di by dt snubber is required. For gate current, high gating power is required. There is long switching times due to turn off tail. So, therefore, switching loss is higher, which limits the operating frequency. It does not have current limitation facility, that is why it limits the forward bias SIP operating area. GTOs are widely used in motor drives, static VR compensators, AC/DC power supplies, force commutated voltage FET thyristor inverters. MOS Turn Off Thyristor. Its symbol is shown in the figure. It has two gates. One is turn on gate, second is turn off gate. This device is developed by Silicon Power Company. It is a combination of GTO and an MOSFET. Structure is as shown in the figure. In addition to PNPN structure, there is FET structure is also added, which is inbuilt. If we see the structure, it has ASCR structure plus FET structure. So, its equivalent circuit, one can say it is a thyristor with FET as shown in the figure. So, left hand side equivalent circuit is thyristor based and second is transistor based. Its turn on is similar to GTO. By applying gate current pulse to the turn on gate like GTO, we can turn on the GTO. Turn on pulse will trigger Q1, that is NPN transistor, which further drive the PNP transistor latching the MTO. MTO turn off. To turn off MTO, a positive voltage pulse is applied to the MOSFET gate. After applying positive gating pulse, MOSFET will turn on, shorting the emitter and base of NPN transistor. It stops the latching process. So, its turn off is much faster than GTO. Like GTO, it also has turn off tail. So, it limits the operating frequency. MTO has higher dV by dt, hence requires much smaller snubber components. Advantages of MTO: high power rating, generally 10 kilovolt, and high current rating also. Fast switching speeds, one can operate this up to 5 kilohertz. Higher dV by dt, hence require much smaller number components. Cost of gate driver power is low as compared to GTO because of voltage drive to turn off. These are widely used in voltage source inverters, flexible AC line transmission, AC/DC motor drive. There are many applications apart from this. The next is emitter turn off thyristor. So, it has also two gates, turn on gate and turn off gate. Its symbol is as shown in the figure. Its structure is SCR structure, that is PNPN structure with two MOSFETs, one PMOS and NMOS. Gate 1 is called as turn on gate, gate 2 is called as turn off gate. Its equivalent circuit is shown as shown in the figure. ETO can be turned on by applying the positive voltage gate pulse to the gate G1 and G2. ETO can be turned on by applying positive pulse to gate G1 and G2. By applying gate pulse to the turn off gate, the transistor M2, that is NMOS, will turn on, which is in series with thyristor. At the same time, another transistor, that is M1, will turn off. The injection current into the GTO gate turns on the ETO. To turn off ETO, negative voltage pulse is required for turn off gate. After applying the negative gate pulse, NMOS will turn off, which is in series with thyristor. Therefore, ETO will turn off. If you see the turn off gate and turn off transistor, so turn off transistor is in series with normal GTO. The advantage of ETO is that there is no high voltage stress on MOSFETs, even though high voltage is applied across the ETO. It has one disadvantage. Since NMOS is in series with GTO, so additional voltage drop during turn on will be there. So, that is 0.3 to 0.5 volt. So, which increases the power dissipation across ETO. Like GTO, ETO has long turn off tail, which limits the high frequency operation. ETO advantages. ETOs are available for higher powers. It has fast switching speed. It is low cost device as compared with others. Gate drive power requirement is low. Wide reverse bias shape operating area. Important is that snubberless turn off capability. Most important advantage of ETO is that it has inbuilt current sensing capacity. So, it simplifies the overcurrent protection. It is capable of parallel and series operation. So, these ETOs can be used in VSIs, FETs, AC/DC motor drives and static synchronous compensators, that is STATCOM. The next device is IGCT, that is integrated gate commutated thyristor. IGCT, which is introduced by ABB in 1997, it is a gate commutated thyristor with multi-layered PCB gate drive. Its symbol is shown in the figure. Basically, it is a high voltage, high power, hard driven asymmetric blocking GTO with unity gain. Basically, it is a high voltage, high power, hard driven asymmetric blocking GTO with unity turn off current gain. Structure of the IGCT is as shown in the figure. It is a cross section of IGCT. If you see this cross section, it is similar to GTO. It has integrated reverse diode as shown in N plus N minus P region. So, it is the right side. So, this side is also called as diode side. Left side is called as GTO side. N buffer layer relieves the voltage stress across the N minus layer. There is also thin lightly doped anode P layer as shown in the figure. Equivalent circuit of the GCT is shown in the figure. It is similar to GTO. Unity gain turn off gain, that is beta m is equal to 1. The meaning of this is, if controllable anode current is 3 kiloampere, it means it will require turn off current minus 3 kiloampere. A very fast and large gate current pulse of full rated current will be required to turn off the GCT. So, that is why drive is necessary. The drive is inbuilt in IGCT. So, it will turn off the thyristor within 1 microsecond because of such high large current pulse. Due to the large turn off pulse, due to a very fast and large gate current pulse of full rated current, IGCT will turn off within 1 microsecond. It ensures a faster turn off. So, turn on is similar to GTO by applying high current pulse to the gate. So, it will turn on the NPN BJT. To turn off, it will require high gate current pulse with very low gate cathode voltage. Generally, gate cathode voltage which is used, that is 20 volt only. Due to high di by dt, NPN transistor totally turns off within 1 microsecond. Effectively, the anode side PNP transistor left with an open base and turn off almost immediately. Turn off sequence is shown in the figure. So, turn off sequence can be visualized as shown in the figure. Initially, both transistors are in on state. When turn off pulse is given, so Q1 will turn off immediately and there will be only PNP transistor with base open. So, therefore, P2 will also turn off. So, this is the left hand side is the conducting state, right hand side is off state, in between this is the transition state while turn off. Gate drive, due to very short duration pulse, the gate drive energy and drive consumption is greatly reduced. Drive power requirement is decreased by a factor of 5 as compared with the GTO drive. It will require a special mechanical and circuit design because for fast rising pulse, the gate inductance should be low, generally less than 3 nanohenry. So, it is shown in the figure. Advantages of GTO over GTOs are listed here: low conduction drop, high turn on di by dt and turn off dy by dt, low gate driver loss, faster switching. Because of that, it will permit the snubberless operation. high switching frequency of operation than GTO. Disadvantage is high cost. It is due to the low inductance housing design. Second is high cost is associated with low inductance circuit and high current design for the gate driver. Applications in high power converters in excess of 100 MVA, static VAR compensators. They are also used in converters for distributed generation such as wind power. MOS Controlled Thyristor. The symbols of MCT is as shown in the figure. There are two types of MCT, PMCT and NMCT as shown in the figure. These are the symbols which are shown for PMCT. PMCT's structure is shown in the figure. Now, if we see the structure of the PMCT, it is NP-NP structure. The figure shows the equivalent circuit of MOS Controlled Thyristor. It has two MOS, PMOS and NMOS along with regular transistors Q1 and Q2. PMCT, it is the NP-NP structure represented by NPN transistors and PNP transistor Q1. MOS gate structure can be represented by an P-channel MOSFET, that is M1, and N-channel MOSFET, that is M2. Due to NP-NP structure, anode serves as a reference terminal. It means the gate signal has to be applied with respect to anode. It has micro cell construction. About 1 lakh cells similar to shown in the equivalent circuit are parallel to achieve the desired current rating. Each cell consists of a wide base NPN transistor and narrow base PNP transistor. Each PNP transistor in a cell is provided with NMOS. It is must to provide higher current for turn off. Around only 4% of PNP transistors are provided with PMOS because to turn on current requirement is not high. Figure shows the equivalent circuit and the gate drive pulse which is required to turn on and turn off the MOS thyristors. So, 14-volt pulse is required across gate and anode to turn off the thyristor. Minus 7 volt is required to turn on the thyristor. MCT turn on. MCT can be turned on by applying negative pulse to gate and anode, that is VGA is minus 7 volt. By applying negative pulse, M1 will turn on, which will drive the cathode transistor Q1. Q1 will drive Q2 and it will turn off the MCT. To turn off, positive pulse is required across gate and anode. By applying positive gate pulse, NMOS will turn on and emitter base of Q2, that is PNP transistor, will short, turning off the Q2, the thyristor will turn off. The advantages of MCT: low on-state voltage, fast turn on time, fast turn off time, low switching loss, high gate input impedance. These are the advantages of the MCTs. There are few disadvantages. it has limited SAP operating area. A snubber circuit is mandatory in MCT converters, and most important advantage, it has complex geometry. So, fabrication is difficult. MCT has not gained widespread acceptance due to IGBT, hence these are not widely used. Next is static induction thyristor. The symbol is shown in the figure. It is introduced in 1960s. It is also called as field control diode, FCD, or field control thyristor, FET-CTH. These are the other symbols. The structure of SITH is shown in the figure. It is a minority current drive device. It consists of a JFET structure with an additional injecting layer, as shown in the figure. It is essentially a PIN diode, that is PIN diode, with a gate structure that can pinch off the anode current flow. It can be turned on by applying positive gate cathode voltage. Applying positive gate voltage, PIN diode turns on, which injects electrons into the channel. It results in large conductivity modulation. Because of that, it results in low on-state resistance. Therefore, low on-state voltage even at larger currents. So, while turn on, JFET is used in a bipolar mode JFET, that is BM-FET mode. Now, thyristor turn off. It is turned off by applying large reverse bias across gate and cathode. Due to large reverse bias, the depletion region of the gate junction grows and pinches off the channel. It prevents the current flow in the channel. Due to addition of PN junction at anode, SITH, that is static induction thyristor, blocks the high reverse voltage. It does not have regenerative turn on and turn off, that is, it does not latch on or off. If the device is on, removal of the gate drive voltage will cause the device to turn off. Advantages: it has fast switching time, high dB by dt, voltage rating up to 2.5 kV, current rating limited to 500 ampere. Disadvantage is it is a highly process sensitive device. Small perturbation in the manufacturing process would produce major changes in the device characteristics. These are about the turn off thyristors we have studied. Till now, we have studied the conventional thyristors and turn off thyristors. In all these thyristors, the main current is unidirectional. Now, we will be studying the thyristors which are having the bidirectional control and bidirectional current. In general, there are two types of thyristors which are widely used. First is TRIAC. It is known as bidirectional triode thyristor, and second is bidirectional phase control thyristors, BCT. TRIAC, the bidirectional triode thyristors. It is an abbreviation of triode for alternating current. Its symbol is as shown in the figure. Since it is a bidirectional device, terminal cannot be designated as anode and cathode. So, terminals are designated as MT1 and MT2, that is main terminal 1 and main terminal 2. The structure of the TRIAC is shown in the figure. From this figure, one can say that TRIAC can be considered as two SCRs connected in anti-parallel with common gate. The structure, the equivalent circuit is as shown in the figure. Figure shows the IV characteristics of TRIAC. So, from the characteristics, it is evident that it works in first and third quadrant with control. So, TRIAC can be controlled by gate current. So, there are various parameters which are shown in the figure. Now, we will see the turn on. If terminal MT2 is positive than MT1, it can be turned on by applying gate current. The polarity of gate current is not important. Gate current may be positive, may be negative. If MT2 is negative than MT1, it is turned on. If MT2 is negative than MT1, then it is turned on by applying gate current. Here also polarity is not important. Gate current can be positive, can be negative. According to this turn on and turn off mechanism, it is evident that thyristor can be used in different modes. These are modes which are defined as follows and shown in the table. So, among these four modes, mode 1 to mode 4, mode 1 and 3 has high gate sensitivity. Hence, these modes are preferred for the operation. Once the TRIAC is on, the gate signal can be removed and TRIAC will remain on until the main current falls below the holding current. It is similar to conventional thyristors. So, there are advantages of TRIAC. Control is easy, circuit size is reduced. TRIACs are basically used for low power. They are used for phase control. So, that is why these are used in AC voltage controllers. TRIACs are advantageous because of low cost and easy control. Limitations of TRIAC is TRIACs cannot be used for high power because of technological limitations. For high power, there was no bidirectional device. Nowadays, one device is available, that is bidirectional phase controlled thyristors, BCT. Its symbol is shown as in the figure. There are two thyristors which are inbuilt and anti-parallel, thyristor A and thyristor B. So, no gate terminal names are given till today. Figure shows the schematic view of the wafer. So, it is basically used for the requirement from high power applications. So, BCT is basically phase control thyristor, but bidirectional. So, generally one wafer is used for fabricating one bidirectional control thyristor. So, figure shows there are two thyristors, that is A thyristors and B thyristors. A thyristor on right side, B thyristor left side. The cross section of the BCT wafer is also shown in the figure. Major challenge in the integration of two thyristors is to avoid crosstalk between the two halves. A major challenge in the integration of two thyristors is to reduce crosstalk between two thyristors. Region 1 and region 2 as shown in the diagram are the most sensitive with respect to surge current. The maximum voltage rating of BCT is 6.5 kilovolt and current can be as high as 3 kiloampere. BCT has two gates, one for turning on the forward current and one for the reverse current. The thyristor is turned on by current pulse to its gates. BCT has two gates. These are used to turn on the thyristors, one for turning on the forward current and one for the reverse current. That is, one to turn on A and other to turn on B. Thyristor is turned on by applying the gate current to the corresponding thyristor. It is turned off if anode current falls below the holding current due to natural behavior of the voltage or current. It is similar to conventional thyristor. It is advantageous for high power applications, advantages of the BCTs. BCTs are highly reliable, so the cost of the drive is highly reduced. It has advantages of the improved volume consumption and reduced part count as compared with the conventional thyristor drives. These are widely used in 4-quadrant DC drives, static VR compensator, 3-phase AC static switches and soft starters for asynchronous machines. Let us summarize this. In this module, we have taken a review of conventional thyristors, turn-off thyristors and bidirectional thyristors, in which the conventional thyristors are of two types. One is phase controlled thyristors, others are fast thyristors. Fast thyristors are almost asymmetric. In case of turn-off thyristors, there is wide variety, but most of the thyristors are based on the GTOs. In turn-off thyristors, there are two thyristors, that is MCT, MOS Controlled Thyristor, and SITH, that is static induction thyristors. The principle of working is different than the GTOs, but these are not much popular in the power electronics community. Lastly, we have seen the bidirectional thyristors, mainly TRIACs and BCTs. In this, TRIACs are used for low power applications and BCTs are basically used for very high power applications. Thank you.